Hello and welcome back to the channel. I'm Tajleen Singh and we are back with a new video. Today's problem is partial digest problem or the turnpike problem. Well, let's get straight to it. The problem statement is given all the pairwise distances between the points on the line, reconstruct the positions of those points. The input would be a multi-set of pairwise distances L containing NC2 integers. The expected output would be a list of n integers such that delta x equals to L. Well, let's look at a toy example to understand the problem a bit better. As we can see, we have a line on the positive side of the x-axis. The points marked are 2, 3, and 5 right here. So we have 2, 3, and 5. Given the different segments of this line, we need to recreate this line and the points 2, 3, and 5 on it. Well, let's see how. The very first question is how to calculate delta x. Well, let's get to it. So we have the points 0, 2, 3, 5 on the line given to us. Okay, and we would write 0, 2, 3, and 5. Similarly here 0, 2, 3, and 5. And then pretty quickly we would just want to look at the upper half of this matrix. So we'll let this go. And here we get, we just take the differences and obviously take the absolute of them. So we get 2, 3, and 5. 2 and 3 is 1, 2 and 5 is 3, then 3 and 5 is 2. And then we sort this down, and this would actually give us the L. So we get 1, 2, 2. Sorry, this would give us delta x, or L for right now, whatever we want to call, because this is the absolute solution. So we get 1, 2, 2, 3, 3, and 5. As you see, we have just sorted it. In computer science, this is very easy to get. So you do for I in range length of L, and then for j in range I, and then you just take the then you just subtract them and take the absolute of them and just append them into the list, and then finally just sort the list, which is again in Python a given function to you already, so you don't have to worry about that. And that's how you would get delta x if at any point you have to calculate delta x. So let's get to a solution, brute force way of doing it. So here we see, and we'll take the same example again, which is 0, 2, 3, and 5. We have the function called another brute force PDP, which is partial digest problem, with the inputs required as L and N. So N is 4 as 0, 2, 3, 5. N is the number of points, and then L would be 0, 1, 2, 2, 3, 3, 5. And as you see here, we have added 0 as one of the inputs in the L. So how do we recreate from this the whole part again? So we take M, which is the maximum element in L. So for us, M would be 5 right here. And then for every set of n minus 2 integers in 0 to x2, x3, up to xn minus 1, and then M, we take from L. So basically what we have is this. We have something as 0, and then since our n is 4, n minus 2 would be 2 spaces, so we'll have 2 spaces, and then we'll have M, which is 5. Now what we do is we use all these numbers pairwise again. 0 we may choose, or we can just let it go because 0 is already included right here, as we can see. And then M is also included, so we let go of these two, and then we start picking the sets of integers pairwise because we have 2 spaces. So the pairs would look something like this. Let's just take some examples. 1, 2, 1, 2. So this is 2, 1, let's say, and this is 2, 2. So we have 2 different 2s again. We would have to go through both of them. We can make a dictionary and check for duplicates. That would be a way to save time. And then we have a 1. Let's say we have 1, 3, 1, 1, 3, 2, 1, 3, 3. Let's just turn on DND for a bit. Pretty nice. So we have 131, 132, 133, and then 135. Going forward, we'll also have 2, 2, 2, 3, 2, 3 again, and all of these sets. And then one which would actually click would be, well, let's just try it inside here, which would be 2, 3. And the first one to be done would be 2, 1, and 3, 1 if you're going pairwise. And then if you're taking randomly, it would be any of the 4 options, which would be, I think, 2, 1, 3, 1, 2, 1, 3, 2, 2, 2, 3, 1, and then 2, 2, 3, 2. So any 4 of these would actually give us the right answer that we're looking for. And then again, we put them in X. We calculate delta X from X given how we did in the previous slide. And then we go ahead to see if delta X is equal to L, which we have right here. So we'll compare them, and if they're true, we'll just return X, and that's all what we want. And if none of these give us a solution, we'll just say there's no solution, because there's literally no solution. But this is a brute force example solution, I think, and it takes quite a lot of time to calculate or go through all of these. So there's an easier way of doing this, and let's take a look at this. So it's technically a smarter way. Let's take a look at this, though a bit elaborate, but again, the more work we do on paper, the less work computer has to do, and the more faster or more quicker do we get the solutions. So let's get to it. Let's look at partial data. So this is the main problem, where we get an L, which we already know, which is, I think, very quickly, I'll just write it down: 0, 1, 2, 2, 3, 3, 5. What I would highly recommend is you would pause the video and go through this algorithm as it is shown on the screen before you actually look at the solution, so that try to understand why we need each step, and then if you can get to the solution, it's pretty nice. Otherwise, I'm here to explain anyway. Let's get to it. We need width, which is the maximum element in L. So for us, width would be 5 right here. Let's fill the things pretty quick. Delete width from L, so I just remove this part right here, thank you. And then X is 0 comma width, so let's just update X pretty quick, so which would be 0 comma 5, and then place L comma X, so we send both L and X. Let's just change colors for L pretty quick so that we can keep track of both of them. So yeah, L is blue, X is gray, and then we send this to place L comma X. So we skip the first 3 steps, as if L is empty, L is now empty, so we won't go into that loop. The next is delta Y. Oh, we need to change the color of L again. I think we cannot have it blue. Let's just make it purple. I don't mind. Okay, so the maximum element in L, which would be 3 for this case. So let's put out 3 here. And then we would change, right? So we would have Y as 3, right? And then if delta Y comma X is a subset of L, so which that means, so we have Y and then we have X. So we basically, what we do is we subtract Y from every element of X, and then we take the mod or absolute of it, and then we just get back that list. So delta Y comma X should return a list, but let's get to it. So for this one, it would be 0 minus 3, and then absolute, which would be 3, and then 5 minus 3 would be 2. So delta Y comma X would give me something like 3 and 2, and then I can check if this is inside L. So if this is present in in L, so I have it as 2 comma 3, so any of these would actually suffice, and we're happy. So we'd go into this, which means we go into step 6 right now, and it says add Y to X. So let's add Y to X and remove length, delta Y comma X. So we remove these and update the L right here. So what we would have is something like this, and we would add Y to X. So X should be updated, so we add 3 to it, and then we sort it. It's just easier to do it. Not necessary though, I think, but it just keeps things very clear, right? So we have done this, and then we call place L and X. So we have an updated L, and then we have an updated X. So you see what's happening is that we're trying to just take one of the major, the maximum numbers, and then we see if, and we subtract it from all of the present points. That would give us the distances. So we'll see if those distances are present, and if they're not present, we'll go back. And once we go back, what we do is we remove that maximum distance from X and then add these lengths. So let's say this part didn't work. Let's assume, well, actually it won't work in the next one. So let's say we have 3 here. Let's go through this actually. So I'm right here, and I go back basically to here. So L is not empty, and then we skip this. We go to 4. So we're already in one. We're already in the recursion part. So maximum element again would be 3. So I have 3 right here, and then it says if delta y comma x is a subset of L. So for this one, we would have, so from here, if we remove that, it actually works for this one. So we get, so 3 minus 0 is 3 again with absolute, and then we get 0 and 2. So this works, and then when we add to it, we basically get 0, 3, 3, 5, and then we remove this. But now the issue is when we take 2, it becomes difficult. So now we update again, and we are at point 7, where X is now 0, 3, 3, 5 and L is 0, 1, 2. But now when we take the maximum element again at point 4 in the recursion part, what we would get is 2, right? So we take 2 and we remove, and we check if delta y comma x is a subset of L. When we do that, we get something like this. So the delta would change. What we would get is here. So we have 2, 1, 1, and then 3. But now you see this 3 is actually not present in L. Hence, we have to go back. Once we go back, what we do is we remove y from x, which was 3. So we remove one of these 3's, and then we add the lengths which were present already in delta y comma x, and then we basically calculate that part again pretty quickly, and we would add it back, right? So that's how it works. And so you will always have different branches, basically 2 branches, and then if something goes back, the points 8 and 12 basically guarantee your return, or the return path back towards that. And then at the end, you would actually get all the points. So at one point in time, L would become empty. You would get the output X, and that would return if there is a solution. And then if there's no solution, it would just return empty, right? So that was PDP. Now the question is that why do we need this? Now this possibly plays some role in computer science, but in bioinformatics, we can say that it is used to recreate DNA/RNA. The restriction enzymes just cut off at different sites, right? So we need to know how we can put it back in. Basically, let's think of it in a way that we had a DNA strand and we used 2 restriction enzymes to cut it into small places. But now we do not know where it was cut actually. And all that we know is that if we have a strand of length X and we have a restriction enzyme, it would cut it into some ratio. But things start getting complicated if we have 2 enzymes, because now it would cut, like let's say the first enzyme would cut here and the second enzyme would have cut here. But now we have different lengths. That, excuse me, that becomes an issue. And this is where this algorithm comes in and allows us to retrace what DNA we already had and where exactly we cut the DNA originally. Congratulations, you've actually successfully completed what we call restriction mapping problem. See you in the next video. If you like this video, please like, share, and subscribe. Thank you, and have a nice day. Bye-bye.